Hello, we are going to do problem number 2 in section 4.3. I wrote here graph f of x equals x cubed minus 12x plus 3, but really they're asking a lot of information. When is the function increasing? When is it decreasing? When is it concave up? When is it concave down? Inflection points, local minimums, local maximums, and this is going to require us to use different facts about the first derivative and the second derivative, and I'll explain that as we go through the problem. I just didn't feel like writing out all of the directions. So for letter A, let's go back to the black pen. For letter A, they want to know when is f increasing. The notation I like to use is f increasing, and when they say when is f increasing, they're looking for the intervals. And I'm actually going to answer part A and part B at the same time. Okay? And I'm going to put a little purple blob over here to the right. And I think I can get everything I need in right there. And the key piece of information I'm going to use is when the derivative is positive, the original function f is increasing. And when the derivative is negative or less than 0, the original function must be decreasing on those intervals. So let's go ahead and take the derivative. They were pretty nice to us. F prime of x equals 3x squared minus 12. And I'm going to go, I know I want to set this equal to 0, so I'm going to go ahead and factor out the 3. And remember, most math problems are designed to work out, and sure enough, I have the difference of two squares. This equals 3 times x plus 2 and x minus 2. So the derivative, f prime of x, is equal to 0 when x equals plus or minus 2. Now, if we were in class, I would make a big deal about this. The key to these problems is making a sign line. I'm going to say that again. The key to these problems is making a sign line for the first derivative, and then later we're going to make a sign line for the second derivative, and you will see why. So here we go. Here's my sign line. Not very straight, that's okay. This is a sign line for the first derivative. I want to know when is the first derivative positive and when is it negative. Well, I already know at negative 2 the first derivative is 0. That's what we just did in the purple blob. I also know at 2 the first derivative is 0. And so notice the two critical numbers divide the real line into 3 intervals. I have the interval from negative infinity to negative 2, and then I have the interval from negative 2 to 2, and then I have the interval from 2 to plus infinity. The good news is all I need to do is pick one number from each interval, and that tells me the sign value of the derivative for all values in that interval. So I'm going to pick negative 3, I'm going to pick 0, and I'm going to pick positive 3. I'm going to do this rather quickly, but you can go ahead and check my work later by watching the video. When you plug negative 3 into f prime of x, when you plug negative 3 into f prime of x, I get a negative, this should be positive. When I plug 0 into the first derivative, I get 0. And when I plug positive 3, I get that f prime is positive. So what this tells me is that the original function is increasing from negative infinity to 2, and or negative infinity to negative 2, and 2 to positive infinity. And because it's negative between negative 2 and 2, I know that the original function must be decreasing on this interval. Isn't that cute? All right, so there we go. Now the other thing I know is, think about this. Let me come back here to my blue. Let's use black actually. Here, this is the sign line for f prime, but on this interval, f is increasing. This interval, f is decreasing, and on the far right interval, f is increasing. So if you think about it, if we read the graph, the sign line from left to right, here we're climbing up the hill. We're climbing up the hill, and right when we get to negative 2, we start going down the hill. Well, that means at negative 2, let me put a C here, letter C, and letter D, that means we have a local max at x equals negative 2, and the local maximum value is f of negative 2. Let's do some quick arithmetic. If I plug in negative 2, that's negative 8, that's 24, that's 16, plus 3 is 19. Double check my work. I'm not good at adding and subtracting. Okay, now let's look at, that's a local max, and then the local min, again, if you start at negative 2, the function's decreasing. You're marching left to right. The function's decreasing all the way until I get to 2. And then once I get to 2, the function starts increasing. So I was going down into the valley and then out. So that means at x equals 2, we have a local min at x equals 2. And the local minimum value, I need to plug that back into the original function. And I plug in 2, that's 8. Minus 24 is negative 16, plus 3 is negative 13. So that's the local minimum value. Okay, so now we're on to letter E, and they want us to find the inflection points. Now, to find the inflection points, we need to determine when the second derivative is 0. So let's go ahead. And where's our derivative? It's way up here. It's 3x squared minus 12. So the second derivative is going to be 6x. Isn't that nice? And f prime of x equals 0 when x equals 0. And again, remember, the key to these problems is making a sign line. This time, I'm going to make a sign line for the second derivative. Oop, let me fix this. I need to put another prime here. Second derivative equals 0 when x equals 0. And I don't need that blob. Let's get rid of that. But I do need a sign line. So here I go. This time I'm making a sign line for the second derivative, and at 0, we know the second derivative is 0. If I plug 1 into the second derivative, I get 1 times 6 is 6, so that's going to be positive over here. And when I plug in negative 1 to the derivative, I get negative 6, and that tells me everything to the left of 0 is negative. Now what this tells me is for the original function, f has to be concave down from negative infinity to 0 and concave up from 0 to plus infinity. This is the original function f. And so there's an inflection point at, so letter E, the inflection point at, well, it's at x equals 0. And when I plug 0 into the original function, I get 3. So this is the inflection point. This is the answer to letter E. go back to the black pen. So now letter F, I'm concave up when the second derivative is positive, and that happens from 0 to plus infinity. In letter G, I'm concave down when the second derivative is negative, so that's from negative infinity to 0. Okay? So we've answered all the questions. Then what you can do is you can piece all this information. I'm going to try to do a little mini graph right in this little area so I can see all my information. It's really hard without seeing the information. So I'm going to try to scooch it right in this little area. Okay? I'm going to graph F. Let me move that line over a little bit. I think this is going to work out just nice. Okay, so here is 1. Let's go over 3. So here's 1. Here's 2. Here's -1. -2. I have an inflection point at 0, 3. Let's go ahead and graph that. There's 1, 2, 3. Maybe went up too high. Actually, I'm going to fix this here in a second. You're allowed to be a little loose with graphing. It's hard to get used to, but once you accept it, you're okay. So, we got to pay attention. I know at -2, I'm at 19. I'm going to call this 19. And at +2, I'm at -13. I'm going to call this -13. Okay? And at 0, it's 3. I'm going to make this 3. Okay? And so here we go. We're concave down and increasing up until -2. Right when I get to -2, I remain concave down, but I'm decreasing. And I'm decreasing when I get to the point 0.03. But once I get to the point 0.03, then I become concave up, but I'm still decreasing until I get to 2. And then I start increasing again, and I'm concave up. And this, my friends, is the graph of y equals f of x. I hope that was helpful.